Okay.
Okay. Homework question. Everybody.
You're so funny.
Haley's
I
just
haven't
like,
pulled up on my computer if that's any.
Haley's like,
I saw Floyd look at it.
we all have more questions. We just don't know what they.
Yeah, the homework.
We just don't know what they are
I'm
yet.
looking at it on my computer.
No, I was totally doing that, and I remember having a second.
I have questions, but they are not new. I have already asked them.
Okay. Oh well, but there's still questions.
I mean, okay. So this iteration okay, for number one.
Yeah.
This iteration matrix, there's one for B, and we're supposed to come up with the iteration matrix for A.
Okay.
In terms of, right? Is that what
yes.
we
Yeah.
are trying to do?
Yeah.
Based on this, okay, so I have a similarity transformation, A equals, and then B equals, and then I replace A and B in each of those with its D, O, and U.
Right.
And we're supposed to use that to come up, to come up with the iteration matrix for A. But I can't. I don't know.
Okay.
I don't know.
So the idea is in your iteration matrix for B,
Mm-hmm.
you have these parts, the D, L, and U for B. You can so then you can try writing them in terms of the corresponding parts for A.
Oh, I think I see what you're saying now.
Okay.
So, but we don't know what's equal to what, though. You said according to their corresponding parts.
Yeah, so the thing is, here is where you have to take into account the fact that your similarity transformation, your D, is a diagonal matrix.
Okay.
That assumption needs to be used.
Okay.
Or the whole thing falls apart. Okay. All right, so at least somebody has some homework questions.
Dr. Lambert.
Yes.
Sorry. Keely is here if you want to ask her.
Oh, yes. Kelia, I don't know if you saw the email I sent to all the GTAs. Are you planning to sign up for any hours during the summer?
You realize, you know,
That's some graduate school. Or,
That's right. I did see that. I guess if I'm doing research, should I say yes?
yeah, if you're going to be signed up for like a 691 or something, then yes.
Okay, so I need to send you an email, right? Or I'm telling you now.
Go ahead and send me an email. But yeah,
Okay.
I just want to try to. You're the last one I don't have info for, so.
I know, and I guess I should have talked to Dr. Cole. I didn't know how she wanted to do it for this summer.
Oh, okay.
Because I really, okay. All right, I'll let you know.
Okay, thanks.
Thank you.
Okay. And are there any other homework questions? Yeah, but only pays for tuition, there's no stipend, so it's a matter of getting his own hours or whatever.
you actually heard him. He like whispered. I didn't even hear him.
Yeah, I can hear him. So, do you have a question?
Yes, for number 3, what is the relationship between M, N, and A?
All you know about, okay, so the problem 3 is that A is equal to M minus N. So the idea is it's a general stationary iterative method that presumably will be convergent for a general matrix. But so that's the only piece of information that you need to use for part A in particular.
For number 2, for the third one,
Yeah.
the fx is supposed to be equal to 0, right?
Right. But you're right-hand side of your system of equations is not going to be 0 because in your derivatives, you're going to have some boundary values that are non-zero. And those terms need to be moved to the right side. And that's why, so even though your right-hand side of your differential equation is 0, your right-hand side of your linear system will be mostly 0, except the first and last elements will have something. And this is why I talked about this in class a while back, about how to set up these kinds of systems. That you're going to have boundary terms that will be moved to the right side.
So we just need to use the two iteration and equations formulas given in.
Right. Yeah, because you're going to use Gauss-Seidel. Yes. So from the differential equation, but using finite differences, like described in section 5.2, you're going to set up this system of equations, and yeah, you'll apply SOR actually.
Okay, so we format A from the finite difference method.
Yes. Yes.
Then we plug this into the two iteration equations.
Yes.
But I get weird result.
Oh, you do. Okay. Weird. How?
So what's the range of omega?
Oh, omega has to be strictly between 0 and 2.
0 and 2.
Yeah, otherwise SOR has no chance of converging.
Okay, try again. Thank you.
Alrighty. Bless you.
Thank you.
Yeah. Okay. See, here are some questions. Any more? Okay. So now we're getting into the final part of the course about eigenvalues. So this will last us to the end of the semester. And I've gone over some basics of eigenvalues already. Now we'll establish a more solid foundation on which to build algorithms, and using some of the pieces that we've seen lately, like household reflections and image rotations. All that stuff's going to come back to haunt us too. Okay. All right. So. So first the definition, a times x is equal to n times x. A is n by n. X is an eigenvector. That must be non-zero. And lambda is a scalar. That is an eigenvalue, and that could be a real or complex number, even if matrix A is all real. Okay. So here's our definition for eigenvalue and eigenvector. We also have a left eigenvector. So similar idea, except we're just multiplying by vectors on the opposite side. So lambda times the Hermitian transpose of a vector y equals that same vector times A multiplying on the left. And to refresh your memory, the Hermitian transpose of a matrix or vector is the transpose and then also the complex conjugate. That's the bar. All right. So we have left eigenvectors and right eigenvectors, but when I say eigenvector, just by itself, I'm just referring to a right eigenvector. Okay, and there's one simple relationship between the two, and that is since y is a left eigenvector, of A, we can also say that if I take the Hermitian transpose of both sides, then I get A Hermitian transpose Y is equal to lambda conjugate times Y. So any left eigenvector of A is a right eigenvector of a Hermitian transpose, where you just take the complex conjugate of the corresponding eigenvalue. Okay. In fact, it can also be seen that the for a let's see, any complex matrix, real or complex matrix, the eigenvalues of A and its transpose are the same. Okay. Now, as far as how we can characterize these eigenvalues, this is something that I've shown you before.
Did you say that when you call it an eigenvector, it's assumed right or left? I can't remember.
Oh,
If you
right.
just say, okay,
Yeah.
that's what I thought.
Okay.